Swayam Prabha, Digital India, Educated India.
Hello students, welcome to the class. So today we are going to discuss about 2,3 sigmatropic rearrangement reactions. So of course we have discussed so many other sigmatropic rearrangement reactions in the previous classes like 1,3, 1,5, 1,7, 3,3 type of sigmatropic rearrangement reactions. So this is not that different from other sigmatropic rearrangement reactions. So any sigmatropic rearrangement reaction would involve the migration of the sigma bond either alone or along with the group attached to its termini from one position to the another position within the same molecule via a cyclic transition state in a concerted manner is called as sigmatropic rearrangement, right? So that information we have gone through, and then 2,3 is again the same type of sigmatropic rearrangement reaction. So where the migration of the sigma bond, the new location of the sigma bond is to the second and third position within the same molecule via a cyclic concerted manner. So how we can define this 2,3 sigmatropic rearrangement reaction means, so it is also a thermal sigmatropic rearrangement reaction similar to that of the 3,3, that is Cope rearrangement or Claisen rearrangement. 2,3 sigmatropic rearrangement is also a thermally driven sigmatropic reaction. Okay, so it is symmetrically allowed under thermal conditions. That means, so it is seen in the case of allyl molecules. Who discovered or who studied this kind of examples means Professor Baldwin is the first one. So Professor Baldwin is the first one to discuss about these 2,3 sigmatropic reactions in the sulfur allyl molecules. So a typical 2,3 sigmatropic rearrangement is a thermally driven rearrangement reaction in which you can see the involvement of 6 electrons. And a 5-membered cyclic transition state. What you can see here in this case is you can see the involvement of 6 electrons and a 5-membered cyclic transition state can be seen. Okay. So what is the example which was first observed by Professor Baldwin and which helped us to categorize them as 2,3 sigmatropic rearrangement reactions, which is a part of the pericyclic reactions, is a sulfur allyl molecule. So this is the sulfur allyl system which has shown the 2,3 sigmatropic rearrangement, and it was first observed by Professor Baldwin. So how we need to number this in order to see that it is subjected to 2,3 sigmatropic rearrangement is discussed now. So there will be an allylic system which is connected to a heteroatom like this, and then the heteroatom will have further connection, either the carbon atom or to another heteroatom can be seen. So what happens in the first step is to see the 2,3 sigmatropic rearrangement. Such molecules has to be treated with a base. So this type of molecules has to be treated with a base. So the base, what it can do is it will search for the acidic protons. So you can see the acidic protons here. So it abstracts the acidic protons, so minus H plus, as a result of which you can see the formation of, already sulfur is having a positive charge here. So C2H5 here, CH3 and CH3 and a minus charge here because proton has been abstracted, a plus charge on the sulfur, and then this. So this is what you will be seeing in the first step, which is not a pericyclic reaction. So this step is not a pericyclic reaction, right? So what clearly you can see here is sulfur being a more electronegative atom compared to the carbon atom here is bearing a positive charge, whereas the carbon adjacent to the more electronegative atom is bearing a negative charge, which is quite in an opposite direction what we have seen in the earlier cases. Usually when the carbon atom is attached to a hetero atom, that to a more electronegative atom like oxygen, nitrogen or sulfur, so it usually tends to have the positive charge, whereas the other hetero atom will usually tends to have the negative charge, right? But here in this case you can see the reversal of polarity. So this phenomena can also be called as unpolang phenomena. So the reversal of polarity in such systems, which is also called as unpolang phenomena, is quite generally seen in the case of the ylides, whether it may be a sulfur ylide, whether it may be a phosphorus ylide, whether it may be a nitrogen ylide. You can see the positive charge on the hetero atom, which is more electronegative than the carbon, and the carbon is supposed to get the negative charge in these systems. Okay. So now the actual thing happens. From here the pericyclic reaction starts. So what is the pericyclic reaction you can observe here is 2,3 sigmatropic rearrangement, right? So how the numbering should be given means the saturated carbon atom which is attached to the hetero atom should be given 1, 2 and 3. This is quite similar to the allylic system which you have seen either in the case of the Cope rearrangement or sometimes in the Claisen rearrangement, right? So 1, 2, 3 is given. So now this portion of the sigma bond which is migrating, this is the sigma bond which is supposed to migrate. So is also started with number 1 and this number 2, right? So now this sigma bond is entirely moving from 1, 1 position to 2, 3 position. So how it is happening is, so this is attacking the third carbon atom, this pi bond is shifting over here, these electrons are moving on to the sulfur atom because it is having the positive charge. So this particular step can only be called as the sigmatropic reaction or the pericyclic reaction. So what is the number? The order represents where the sigma bond is migrating. So if the order which is shown on the top of the arrow is like 2, 3, the new position of the sigma bond is 2 and 3, right? So therefore, how the product will look like now? So a new double bond is here, this is 1, 2 and 3, right? So this has 2 methyl groups already, and now a new connection is being formed between 3 and 2. So this is 2 which is connected to the sulfur atom. So the sulfur is already having an ethyl group here, C2H5 here, and then this is connected to what? 2 is connected to this one. So the second carbon is connected to this one which is having a double bond and then 2 methyl groups. So this will be the product which is seen in the case of the first example which was observed by Professor Baldwin. So in the example explained here, so it is understood like although the sulfur and carbon atoms are almost same, comparably same with respect to the electronegativity, and unlike the oxygen carbon or nitrogen carbon, so sulfur is more nucleophilic because of its bigger size and polarizability and its lone pair being always available for donation. So the positive charge on the sulfonium sulfur or sulfoxide or maybe sulfone sulfur confers the acidity on the hydrogen attached at the alpha carbon atom.
So, this is the reason why you could be easily observing the Ampolung phenomena in the case of sulfur ylides.
Okay. So, in a generalized way, if we want to see the sigmatropic rearrangement, that is 2, 3 sigmatropic rearrangement, we can see like this. So, in general, the sigmatropic 2, 3 sigmatropic can be seen like this. So, what is here is a x and y, let it be. Okay. So, if it is connected to some groups, that is absolutely fine, not an issue. So, here X can be a heteroatom like oxygen, sulfur, nitrogen, and Y can be an oxygen, that is a heteroatom, or it may be sometimes a carbon atom also. Okay. So, we will see both the cases. So, now this becomes 1, 2 and 3, this is 1 and this is 2. So, the must condition you have to see is, if Y is an oxygen atom, of course, it will have the lone pair of electrons, and if the Y is a carbon, it should have a negative charge, right. So, then the things will be in favor of the 2, 3 sigmatropic rearrangement. What will happen? So, this will attack here, this will move here, and this comes on top of the X. So, therefore, under thermal conditions, 2, 3 sigmatropic rearrangement takes place, resulting in the formation of Y and then X. X is now having a pair of electrons, excess electrons, that is shown here. So, or dash. So, how this is happening means, it is happening via a 5-membered cyclic transition state in a concerted manner. So, that cyclic transition state can be seen this way. This is Y and this is X. So, the sigma bond which is existing between the first carbon atom and the X is slowly vanishing, right. So, the lone pair of electrons which are seen on the X is slowly moving on to the third carbon atom, and then the pi bond which was existing previously between 2 and 3 is slowly moving towards 1 and 2, right. So, this is the cyclic transition state which can be seen during the reaction, right. So, what if the Y is a oxygen atom, or X double bond Y and then there is a double bond. So, two different types of generalizations can be seen for this, 1, 2 and 3, and this is 1 and this is 2. So, now under thermal conditions via the cyclic transition state, it undergoes 2, 3 sigmatropic rearrangement and then shows this product Y and then X. So, this is what going to happen in the 2, 3 sigmatropic rearrangement. So, what are the examples that are most studied in the 2, 3 sigmatropic rearrangement reactions are means ylides. So, ylides are the molecules which are capable of showing the Ampolung phenomena. So, what we have discussed in just a moment ago, like, so the heteroatom which is more electronegative carrying the positive charge, while the carbon atom adjacent to it is having the negative charge. So, if you see the polarity reversal in a molecule and then the same molecule with positive and negative charges within it and quite stable is called as ylide molecule, So, these ylides are good to show the Ampolung phenomena. So, what kind of ylides? So, any ylide molecule which are having an allylic system as a substituent on it over the heteroatom are quite good enough in performing the 2, 3 sigmatropic rearrangement. Again, alpha allyloxy group if present, so then it is also fine to perform the 2, 3 sigmatropic rearrangement. So, if not, if the ylide system is having an allyl sulfoxide group, so then also it is fine for the 2,3 sigmatropic rearrangement. So, ylides having the allyl group function are alpha allyloxy group or allyl sulfoxides or allyl selenoxides. So, if any of these are in coordination with the ylide group, so then they are all capable of performing the 2,3 sigmatropic rearrangement reactions. So, what if the X is a sulfur atom and the Y is a carbon atom? So, if X is a sulfur atom and Y is the carbon atom, we call such systems as sulfonium ylide systems, which can perform the 2,3 sigmatropic rearrangement. For example, if you want to see this, so the sulfur is attached to an R group, R may be anything, and an allyl group here. So, in this case, the R group is this one. So, this is the R group, right. So, now, so in the beginning what we need to do is we have to impart some negative charge into the system. So, for that, if you treat the molecule with a base, in this case the tertiary butoxide, potassium tertiary butoxide, what happens is it will abstract a proton from the acidic carbon atom. So, once it abstracts the proton, so you can see the negative charge adjacent to the positive charge on the sulfur atom, which stabilizes the molecule. So, this is the sulfonium ylide molecule. This is the sulfonium ylide molecule. Now, the numbering has to be started with the saturated carbon atom, which is attached to the hetero atom. So, this takes the 1 and 2 and 3. Similarly, the other end of the sigma bond, which is migrating, should be given also 1 and 2. So, this is 2, right. So, under thermal conditions, so the same molecule will be subjected to 2,3 sigmatropic rearrangement. So, how it is going to happen? This attacks here, this pi bond moves over here, and this sigma bond will be taken up by the sulfur. As a result of which, the sigma bond between sulfur and this carbon atom, saturated carbon atom, is migrating to 2 and 3 positions, or so this is the 1 and this is the 2. So, now this second carbon atom is attached to the third carbon atom of the allylic system previously, right. So, 3, which is connected to 2 and then 1. So, now the pi bond, which was previously between 2 and 3, is now seen in between 1 and 2. So, this is the product. So, similar to that of all the other pericyclic reactions, 2,3 sigmatropic rearrangement reactions, whether they are happening in the sulfonium ylides or whether they are happening in the nitrogen ylides or some other molecules. So, all of them will be highly stereoselective in nature. So, the reason for the high stereoselectivity of these reactions is they are happening in a concerted cyclic transition state manner. So, next example, you can see the ring expansion of the cyclic sulfur ylide. So, this is the cyclic sulfur molecule, sulfur containing molecule, right. So, this upon treating with a strong base or with the azo molecule C2H5 twice, under instead of a base, if you treat it with a copper catalyst, in the first step what happens is this will be connected to the sulfur atom, because sulfur is having a lone pair of electrons. So, nitrogen will be removed from this. Yes, which is now connected to the carbon, which is having COO, C2H5 as well as COO, C2H5, and then this, because of which you will be seeing the negative charge on this carbon atom and this one. So 1 and 2, this is 1, 2 and 3. So there is every possibility of showing the 2,3 sigmatropic rearrangement. So now what is happening here is this particular sigma bond which is closing the ring, 5-membered ring, is breaking. So that means this is no more a 5-membered ring, right? So what is happening here is the ring is expanding. So if this bond is not there, for example, what is happening now? How many atoms are involved here? A new sigma bond is formed between this carbon atom and this carbon atom, right? So now 1, 2, 3, 4, 5, 6, 7, 8, including the sulfur atom, you are able to see 8-membered ring here. Right. So this is the sulfur, adjacent to which is the carbon having the ester groups COO, C2H5. So this is the second carbon atom here, right? So which is now connected to the third one, 3, 2, 1, and new double bond is there here. So this is the product with a ring expansion. So this is a 5-membered ring, and now after the reaction 2,3 sigmatropic rearrangement, you are able to see a 8-membered ring structure there. Instead of these reagents, for the same molecule, if we use the allyl iodide, so allyl iodide if we use in the presence of a catalyst, so now what happens is this attacks here and iodine moves out, I minus. Yes. So this is what you will be able to see. This is there already. Yeah. Any side we can have it, right? Now, so sulfur has got the positive charge now. This, upon treating with a base, will abstract a proton and then generates a minus charge, right? So once it is there, now it is capable of undergoing 2,3 sigmatropic rearrangement. So definitely the ring expansion takes place, and again what you can see here is this is 1 and 2 and this is 1, 2, 3, right? So this is what happening. So again what is happening? 1, 2, 3, 4, 5, 6, 7, 8. 8-membered ring is forming. So what is there here? An allyl group. So where is the double bond position? Between 1 and 2. So here. So this is the product with the ring expansion. So next thing is, if X is equal to N and Y is equal to C. So you call this as nitrogen ylides. Nitrogen ylides involved in the 2,3 sigmatropic rearrangement. So similar to that of the sulfonium ylides, nitrogen ylides are also able to involve in the 2,3 sigmatropic rearrangements. Okay. So in the case of some of the nitrogen ylides, you can see the ring contraction reactions. Ring contraction. Previously you have seen the ring expansion reaction where the 5-membered sulfonium ylide is converted into a 8-membered ring system. So here there is possibility of ring contraction reaction. So we can go through the example, thereafter we can discuss further. So this on treating with NaH under THF, in the presence of THF. So what thing is, we need to reflux this mixture. So now what is happening here, 1, 2, 3 is there, and then so NaH is a base, so it can abstract the proton, so therefore minus comes here, and then this is 1 and this is 2. So what is going to happen? So this will attack here, and then this comes here, and then this is completely removed, and nitrogen takes away those electrons. Okay. So ring has been opened here between 1 and nitrogen position, the ring has been opened. So now a new connection is being formed. So what it is? So the second carbon atom is attached to this carbon atom, right? So 1, 2, 3, 4 and 5. So how many atoms are there in this? 1, 2, 3, 4 and 5. So that means a 6-membered ring has now transformed into a 5-membered ring, right? So this is the 5-membered ring. What is next immediately connected to this is the second carbon atom. So what does it have? Nitrogen is having already a methyl group, and then the second carbon atom is having COO, CH3, and then this is connected to the third carbon atom, so the 6-membered ring has converted into the 5-membered system. So one more nitrogen containing 2,3 sigmatropic rearrangement is the Somlet-Husser rearrangement. Rearrangement. Okay. So when you can see the quaternary amines, this is a quaternary amine. What kind of quaternary amine? A benzylic quaternary amine system. So this, on treating with a base followed by heating, this on treating with a base followed by heating, you will be able to see 2,3 sigmatropic rearrangement reaction. So this is 1, 2 and 3, and this is 1, and any of these 3 methyl groups can contribute and then lose the proton, as a result of which you will get CH2 minus, and this minus along with this nitrogen plus becomes the quaternary ammonium salt, and then this involves in the 2,3 sigmatropic rearrangement reaction. So we can see this way, N has got plus and this is CH2 minus, right? So now what is happening? This attacks here, this goes here, and this will go here. Thermal conditions, 2,3 sigmatropic rearrangement, double bond is formed here, and now this carbon has formed a sigma bond with this ring, and it is connected to a nitrogen. Nitrogen is having 2 methyl groups, dialkyl benzyl ammonium amine system. So this can always show this internal rearrangement again, and you will get this one. So dialkyl benzyl amine system. So this is the Somlet-Husser rearrangement reaction. Yeah, one good example which was previously asked in the competitive exam can also be discussed here. Double bond O, and then so this is one of the example which was previously asked in the competitive exam. So under the presence of the rhodium catalyst under thermal condition, what initially happens is it generates a carbene. It generates a carbene, double bond O, and yeah. these 2 electrons is nothing but carbene. And if you go back to the basics, carbene is a reactive intermediate and it can exist in either in singlet form or in the triplet form. Okay. So, we do not need that kind of information whether it is in the singlet form or in the triplet form. We just see that a carbene is being generated because of the presence of the rhodium catalyst. It is losing a nitrogen and then you are able to see the carbene here. So, carbene. So, oxygen is already having a lone pair of electron. Now, this will undergo the sigmatropic rearrangement, 2,3 sigmatropic rearrangement reaction. So, the carbenes are electron deficient, so it attacks over here. So, therefore, what you will be getting? Oxygen with a positive charge, double bond O, and because another electron is also coming towards this carbene carbon atom, you will see the negative charge over here. Okay. So, now number it 1, 2, 3 and this is 1 and 2. So, what is happening here? So, this will happen. So, undergoes the sigmatropic rearrangement, as a result of which oxygen is there, double bond O, and now new bond is formed between this. The existing bond is broken between these two and this is the new bond. Previously asked in one of the competitive exam like CSIR. So, if X is an oxygen and Y is a carbon. So, we see such type of things in the Wittig rearrangements. So, specifically 2,3 Wittig rearrangement reactions. So, what is a Wittig rearrangement? 2,3 Wittig rearrangement means the conversion or the transformation of the allylic ethers which are deprotonated to give a homoallylic alcoholic molecule, alcoholic molecules. What do you mean by homoallylic here? Means the carbon which is next to the allylic carbon atom is called as a homoallylic carbon atom. So, if the alcoholic function is on the homoallylic carbon, so the product is also called as homoallylic alcohols. Allylic ethers, so which on deprotonation, so that is on treating with a base like butyl lithium, undergoes deprotonation and results in the formation of deprotonated. So, these are the allylic ethers on treating with a base like butyl lithium. What is going to happen? So, deprotonation takes place at the acidic hydrogen will be captured and negative charge will be generated here. So, this attacks here and this goes here and oxygen will take up these electrons. So, this moves over here. So, under thermal conditions 2,3 is happening, as a result of which the product is this. This is third carbon atom, second, and this is connected to O minus, and then this is pH. Okay. So, this is the product which you are able to see here, and 1, 2, 3, and this was previously 1 and this is previously 2. So, this is the product. Upon treating with or providing a proton, you will get homoallylic alcohols. If X is sulfur and Y is oxygen, this is Mislow Evans. Yes, double bond O and this one. So, 1, 2 and 3, this is 1 and 2. So, any other substituent can also be there. So, what is going to happen here? Under thermal conditions, it shows 2,3 sigmatropic rearrangement because oxygen is having a lone pair. attacks over here. So this is R, which is now connected to oxygen atom, and this. So because these pi electrons are also involved here, so you will get. So this reaction is nothing but Mislow-Evans rearrangement reaction. So these are the different types of 2,3 sigmatropic rearrangements can be seen, where if x may be in the generalized equation, the x may be any heteroatom like oxygen, sulfur or nitrogen, and y may be either oxygen or the carbon atom. If it is oxygen, fine. In the case of Mislow-Evans, you can see the y being oxygen, and therefore there is a double bond between these two. If it is a carbon atom, one thing should be for sure, so it should be capable of getting a negative charge.
So besides discussing all other examples related to the 2,3 sigmatropic rearrangement, so we can also discuss the Mesenheimer rearrangement, which involves the 2,3 sigmatropic reaction. So in the case of Mesenheimer example, so what you can observe here is the X being a nitrogen atom and Y being an oxide. So that means typically Mesenheimer rearrangement talks about the N oxides undergoing the 2,3 sigmatropic rearrangement. So how do you define this Mesenheimer rearrangement? So some tertiary amine oxides having an allylic or benzylic group. So the primary requirement for these molecules to show the Mesenheimer rearrangement is that the tertiary amine oxides which are having an allylic or benzylic group can be subjected to rearrangement upon heating and results in the formation of hydroxylamines. So that is, the tertiary amine oxides having an allylic or benzylic groups rearrange upon heating to give the substituted hydroxylamines is the Mesenheimer rearrangement reaction. In the example quoted as shown in this slide, you can observe that the nitrogen, which is a tertiary nitrogen holding the positive charge and also connected to the electronegative oxygen atom, which is X and Y respectively. So the allyl group having the proton at the allyl carbon atom. So what is happening here? So under thermal conditions, so it is subjected to 2,3 sigmatropic shift and resulting in the formation of the product, which is an hydroxylamine. In the second example also, you can see the similar kind of reaction where the nitrogen is at one end connected to the alkyl group, methyl group, and then the other end of the nitrogen is also connected to the oxygen bearing the negative charge. So this molecule, this tertiary amine oxide, can undergo the sigmatropic shift, particularly 2,3 sigmatropic shift, resulting in the respective product.
So therefore, you will be getting the ylide systems which can involve in the 2,3 sigmatropic rearrangement under thermal conditions to give the respective products. Okay, thank you.